as we could see in the previous examples, or in the previous lectures, I guess I should say, there's a lot of integrals that we can figure out, but they're often very difficult. It's not usually a very straightforward process to find antiderivatives. So for this reason, we often want to kind of ask ourselves if there's any outside assistance that we can look for when we're trying to solve an integral. And the answer is, yeah, there are a few different kinds of outside assistance that you can try to get when you're looking to these kinds of problems. So I want to briefly mention a couple of those, and then I want to talk about what we can do to find definite integrals when those integrals are not necessarily things that we can find antiderivatives for directly, or maybe where we just don't need an exact answer. So the first thing I want to say is when you have to find an antiderivative, whether it's because you're doing a definite integral or just because you need that antiderivative, it doesn't really matter. One of the most useful things that you can do is you can look up a table of integrals. Now, these tables of integrals, there's one at the back of your textbook, which you can access online. It's in the reference pages, I think it is, at the back. But it's a fairly short table. However, it is in there. And there are much better tables, lots more integrals and things like that, that are published in, for example, what is called the CRC. Okay, this pen is supposedly new, but it appears to be completely non-functional. Let's see if we can get it going by shaking it a bit and getting the ink down into the tip. Sort of. Anyway, so the CRC, this stands, or well, rather the CRC handbook. CRC stands for Chemical Rubber Company, and they publish this huge handbook of various things that are useful for engineers, physicists, mathematicians to know. Primarily it's for engineering and chemistry, I guess, but anybody can use it. And when I was a physics student, as an undergraduate, I double majored in both physics and mathematics. When I was a physics student, we would use the tables in the CRC all the time to find antiderivatives. So the thing about using these tables is that they don't usually give you, obviously they cannot give you every single integral in exactly the form that you're going to see it. So instead what you have to do is you look for something that is in the table and looks kind of similar to what you have. And then you ask yourself if you can do a minor algebra simplification or rewrite, or maybe do a simple U substitution to get it into the form that's in the table. So you still usually have to do a little bit of work when you're working with one of these tables of integration, because you still have to make it look like one of the integrals in the table. But the idea is that hopefully the really hard part of the antiderivative will be done for you. So that way you just have to do a small, relatively trivial, and again, relatively, it may still involve a bit of thought and work. But the idea is that, yeah, you look it up in the table, you get it into that form, and that's not too difficult to see how to do. And then they do the hard part of finding the antiderivative, because maybe actually finding the antiderivative might require like integrating by parts and a trig substitution or something like that. So it saves you all of that time. All you have to do is to get it into that format by doing a simple U substitution or something. So using a table of integrals is a really, really useful thing to do. And I strongly recommend it if you're ever out there in the real world and you have to find an antiderivative. It's a really good idea to ask yourself, can I just find somebody else who has basically done this integral for me? Now, obviously, if you're doing integrals all the time, you'll want to have the table with you while you're doing the integrals so that you can keep looking them up. But the truth is that, yeah, you really can often kind of use those kinds of references to do these problems. So while it's good to know all of the techniques that we've gone through, and you definitely should know how to do them, you can sometimes make things easier on yourself by finding something like this. The other thing that you can do sometimes, as a practical matter, is sometimes you can ask a computer algebra system, as it's known, to try to do the antiderivative for you. Now, this is a little bit hit and miss, and the reason is because antiderivatives are very, very tricky. And as a result, computers are usually programmed to give up after a certain number of attempts or something like this. And so if you ask a computer algebra system to find an antiderivative, just because it fails doesn't necessarily mean that it can't be done. It just means that the computer system hasn't been programmed to be clever enough. So you can ask computer algebra systems like Maple or other systems. Derive is another one that's fairly, that one's put out by Texas Instruments and things. There are, there's others out there, of course, and you can ask them to do it, and that's fine. You can even use Symbolab online for free to try to do it. But again, they often fail even when it's possible to do the antiderivative. So we're not going to cover too much about that. If you need to, understand how to use a table, well, get a hold of the table that you're going to be using and get used to looking things up in it. If you're going to use a computer algebra system, then it depends upon which system you're using. And again, you just have to get used to using that particular system. So usually the computer algebra systems are fairly straightforward these days to understand and to work with. So it doesn't take too much effort to get used to those, especially some of the nicer ones. Everything is just entered exactly the way that it looks on the page, and so you just have to learn how to enter it and things like that. Again, though, you want to be careful because it can fail even when it's possible to find an antiderivative. So the next question that we have is, what about if you cannot find an antiderivative, or you just don't need to find an antiderivative? All you need to do is to find some definite integral, and maybe you're doing an application where it doesn't matter if it's exact. Maybe it just has to be approximate. An example of this is a kind of integral that shows up all the time in statistical applications and other applications for that matter, is the integral from A up to B of e to the, this pen is truly awful, to the minus x. Okay, we're going to have to do a different pen, obviously. I apologize for this. The pens around here that I get tend to have massive issues. There we go. This one seems okay. The integral from a to b of e to the minus x squared over 2 dx. Actually, there's usually more factors up here, but you can get it into this form after a u substitution and things like that. Here's the thing. We cannot find the antiderivative of this using the techniques we've had so far. So how are we supposed to find a definite integral like this if we cannot find an antiderivative? The answer is, although the fundamental theorem of calculus is really good for finding definite integrals because it tells us how to do it in terms of the antiderivative, it's not really the only way, at least if we only need an estimate of finding a definite integral. And if we only need an estimate, then one way that we can approximate the integral is going to be the following. We essentially just say, well, let's set up a Riemann sum, and we'll pick a Riemann sum to do, and then we'll calculate that Riemann sum, and hopefully, if we've got our intervals that we cut the thing up into, if they're small enough, in other words, if we use enough rectangles in our Riemann sum, then hopefully our estimate is going to be relatively close to the exact answer. And if all I'm interested in is an approximation anyway, then that might be good enough. Maybe all I'm trying to do is to calculate, for some shape, how much paint am I going to need to cover this shape? Well, I don't need to know down to the very last gram of paint how much. I'm just asking, basically, how many buckets of paint do I buy or something like that. And you can think of other situations where you don't really need an exact answer. You just need something that's close enough. A good example of this, actually, if you saw the film Hidden Figures that came out a couple of years ago, in that, it wasn't exactly an integration problem. It was a differential equations problem, but it's kind of related, that they could not solve, involving atmospheric reentry of their spaceships. And one of the things that they noticed, because the film is about the three women working with NASA to help them with their calculations and things. Well, one of the things that the team working on reentry noticed was actually we don't need an exact answer because we're just birding the thing. We just need to be within a certain tolerance of the correct answer, and we'll still make it through the atmosphere. And so what they ended up doing was just approximating the answer. So they never actually solved the problem exactly. The problem is pretty much not solvable. In fact, I don't think anybody has solved the problem exactly. So in applications like that, a lot of engineering type applications, you only need an approximate answer. You don't need exact answers. The simplest way of doing this is something called the Midpoint Rule. And this is just do a Riemann sum using the midpoints of the subintervals that you cut the thing up into. So we can say the integral from a up to b of f of x dx is going to be approximately equal to the sum from I equals 1 up to n of f evaluated on xi star times b minus a over n, where our xi stars here are chosen to be the midpoints. And how do you find the midpoints? Well, the first midpoint is going to be, you take this, let's call this delta x, and the first midpoint is going to be a plus, let's see, delta x over 2. And then to get up to the IF midpoint, we would multiply this, delta x over 2. And then to get up to the IF midpoint, we shift this over by an additional I delta x's. So that gives me an I minus 1 delta x. So this is where the first midpoint is, and then we keep on going like so. Or a simpler way of writing this maybe is that this is a plus I minus a half times delta x. So those are the midpoints of our intervals, and then we just evaluate these and do this sum. Now, the actual process of doing this is not difficult. It is just kind of tedious. We just have to keep on calculating, repeatedly evaluating the function, and then summing these things up. Now, the great thing is that computers are really good, calculators are really good at doing tedious math like this. So it's fairly straightforward to program a computer to do this kind of thing for us. You might want to try practicing this by hand a couple of times to kind of get the idea of what it's doing, but in practice, you're probably going to use a computer for this kind of thing these days. Because obviously, to get a really good estimate, we need to take n to be a very, very large number. And if we take n to be a very, very large number, well, if I set n equal to 100, I really don't feel like evaluating this function 100 times and then calculating the sum. But a computer can do that in an instant. Well, not an instant, but very, very quickly, faster than we can even really notice. So this is one way of getting an estimate of our integral. Now, there are other ways of doing it. And the problem with this method, this midpoint method, is that the error bound is really, really kind of bad. In other words, we want to know how close does this midpoint estimate get us to our actual correct answer. And there is a result, which we're not going to prove because the proof is somewhat complicated. But if you go on to take a course in what's called numerical analysis, then you'll go through the proof of that sort of thing there. If f double prime of x, absolute value, is less than or equal to k on the interval from a to b, so we're taking that interval where we're trying to approximate, interval where we are trying to approximate the integral, and we are looking at the second derivative, and we want to look at something that bounds the second derivative. Then what we can say is that the absolute value of the error for the midpoint rule is less than or equal to, and let me make sure that I get this correct, it is k times b minus a cubed divided by 24n squared? Yes, n squared. So the problem with this method is kind of that it ends up giving us this sort of like really bad error potentially. So we can ask questions though, like if I want to use a specific, if I want to do a specific definite integral using the midpoint rule, and I need to make sure that the error is bounded below a certain number, I can ask, well, what n do I need to pick to make sure that the error is below that number? So this is actually a very nice result in the sense that if we know our tolerance for error, this tells us how to pick n so that we are within that tolerance for error. As long as we can pick an appropriate, as long as we can find this bound on the second derivative. To give you a quick example of this sort of thing, suppose that we want to know what n do we need to guarantee a midpoint approximation of the integral from 0 up to 3 of, let's say, x cubed dx is within 1 over 1,000 of the correct answer. Okay, sorry, my handwriting's terrible, so hopefully me reading this out allows you to know what I've written down here. So we want to know how to do this, and the answer is going to be the following. Well, we need to find a bound on the second derivative of this function. Now, the second derivative of this function, if I take the second derivative of x cubed, this is the first derivative of 3x squared, which comes out to be 6x. And this is going to be less than or equal to 6 times 3 equals 18 on the interval from 0 up to 3, which is what we are interested in. So what we can say in this case is that my k is going to be equal to 18, because the absolute value of the second derivative is always less than or equal to 18. And then what we can do is we can say, well, in this case, my a is equal to 0 and my b is equal to 3. So what we have is going to be our error I'm going to leave this formula up because I need to use it. Our error is going to be less than or equal to 18 times 3 minus 0 cubed divided by 24n squared. Well, this means that we're going to have to, now I want the error to be less than 1 over 1,000. So I want to have 1 over 1,000 less than or equal to 18 times 3 cubed divided by 24n squared. This means that n squared should be less than or equal to 1000 times 18 times 3 cubed divided by 24. So to get n, I just need to have sorry, there's a better way of writing this down, because I think the way that I wrote it is going to make it very weird to find what we want here. If we take the reciprocals here, this tells me that 1000 is greater than or equal to 24n squared divided by 18 times 3 cubed. So this means that if we kind of solve for the n squared here, we're going to have n squared, and we need to have this thing bounded by what we solved here. I guess it doesn't really matter. The first way that I did this can work too. So we figure out what n squared is going to have to be in order to make this work. And once we see that, we can say, well, that is the n that we need to pick. So I will let you enter into a calculator to figure out what n is going to have to be. And usually it will come out to be some sort of a decimal. So we have to round it up to the next highest integer, because we need to make sure that this is really strictly less than that particular value. So a smaller n than what we solve for isn't allowed, but larger is. And since n has to be a natural number, we want to go up to the next natural number. We don't want to just round it normally. So using this technique, you can make sure that your estimate is going to be within whatever tolerances you need. Maybe that tolerance is to within 1 over 1,000. Maybe it's to within just 1 over 100. Maybe it's to, like, we need it to be to within 63 over 70,000. I don't know. The point is, you can do this in any particular case that you want to. Now, there is another method of doing estimates, which I'm going to just briefly show you here. And this comes from what is known as the trapezoidal rule. The trapezoidal rule is kind of, so from the midpoint rule, we can visualize the midpoint rule in the following way. If I have some integral, definite integral that I'm trying to do here, the midpoint rule says, okay, you cut this thing up into pieces. I'm just going to cut it up into 3 pieces to demonstrate. The midpoint rule is basically throw in rectangles based on the height of the midpoint. That doesn't really line up with the midpoint. There we go. So you put in rectangles based on the height of your midpoint. But another option that we could do to try to estimate this area, and one that seems like it might work fairly well, would be, what if instead of using the midpoint, instead of using rectangles, I try to cover this thing with trapezoids. So for this first interval, I build the trapezoid, which has its vertices at these 2 points, determined by the function at a and at a plus delta x. And then for the next one, I do the same thing. And for the third one, I do the same thing on the third interval. So instead of using rectangles, what if I use trapezoids? Well, in this case, what we're going to be doing is we're going to be doing a sum of these trapezoids. Now, what is this area of this trapezoid? Well, it's going to be f of xi plus f of xi plus 1 divided by 2 times delta x, because we're taking the average height of the function, well, the average of the 2 endpoints, the average of the heights of the edges of this trapezoid. To get that, we take those 2 heights, add them, and divide by 2, and then we have to multiply by the width of the trapezoid. So when you work out what this rule is, it turns out that this is going to give you delta x over 2 times f evaluated at x0, which is going to be a, plus 2 times f of x1 plus 2 times f of xi in general, plus all the way until we get to b, at which point we just have one of those. The reason why pairs show up is because you'll notice that as I sum these together, x1 shows up in the f of x0 plus f of x1, and it also shows up in f of x1 plus f of x2. So it shows up twice, but the endpoints only show up once. Everything else shows up twice. So this is known as the trapezoidal rule because this one relies upon approximation using trapezoids. Once again, you can try doing this for a few basic examples by hand, but if you're going to do this for a large value of n, then you definitely want to just have a computer do it. Now, just like with the midpoint rule, we can get an error bound here for the trapezoidal rule. And let me write down the error bound for you. Give me just a moment here. The error bound is actually pretty similar to the error bound for the midpoint. So, if on the interval a to b, we have the second derivative of x, absolute value less than or equal to k, then the error for the trapezoidal rule is less than or equal to, it's almost the same thing. It's going to be k times b minus a cubed divided by 12n squared. So it's kind of the same thing. It's literally just going to be twice the error of the midpoint rule. And so weirdly, we end up with a bigger possible error when we do the trapezoids versus the midpoints, which might seem kind of surprising, but again, if you go through the proofs, you see why this is. Well, anyway, it turns out that essentially you can kind of convince yourself by drawing some different examples. But here's what I want to say. This is the worst case scenario. And because it's the worst case scenario, it's kind of like in many applications, the trapezoidal rule might give you as good or better an estimate than the midpoint rule. The problem is that it could give you a worse estimate. So we don't really know which one is going to be better ahead of time. However, for a lot of well-behaved functions, it may well be the case that the trapezoidal rule gives you less of an error and thus is better. It's just it could potentially be a worse error. Now, you might wonder what is the next best thing we can do. Because here's what I want you to observe about this method, or the methods that we've looked at. The midpoint rule, and this is quite an interesting point. The midpoint rule comes from taking my function, here's my y equals f of x. I can think of the midpoint rule as the following technique. Okay, I can also erase the y on my axis, but I can think of the midpoint rule as coming from approximating f with piecewise constant functions. In other words, I take a new function that looks like the original function, but it is constant on each piece. So on each interval, it is equal to some constant. And then I integrate that piecewise constant function instead of f. The trapezoidal rule, this is going to be approximate f with a piecewise linear function. What does a piecewise linear function mean? Well, a piecewise linear function is a function where on each subinterval it is equal to some linear function. So this is really the trapezoidal rule because the tops of those trapezoids, if you look at what they are doing, they are actually a piecewise linear function. On each subinterval, they are equal to some straight line, and they approximate your function f. So the natural thing to do is, see, this is approximation with degree 0 or piecewise degree 0, right? Constant functions, those are degree 0 polynomials. So we're approximating where on each interval we treat the function as if it's a degree 0 polynomial. Here, we approximate the function by treating each interval as if it is a degree 1 polynomial. So it's natural to then ask yourself, well, what if we went up to degree 2 polynomials? In other words, what if replacing f with a parabola, i.e. a degree 2 polynomial, on each sub-interval? Well, we can try to do that. In fact, this idea where you try to approximate the function by replacing it with a piecewise parabolic function, so on each interval you get a parabola, this ends up giving you something called Simpson's rule. And give me a moment while I glance at my notes to remind myself what exactly Simpson's rule is, because honestly, I don't use this all that often. So Simpson's rule gives you the following. It says, and you can look in your textbook for fully working this out. I'm not going to go through the derivation of this, but it's done in full in your textbook. The integral from a up to b of f of x dx is approximately equal to delta x over 3 times this entire quantity. F of x0, which, again, remember x0 is equal to a, f of x0 plus 4 times f of x1 plus 2 f of x2. Sorry, I don't need that extra parenthesis there. And then we have plus 4 f of x3 plus 2 f of x4. And it keeps on going like this. So you get a coefficient of 4 on all the odd points of the interval, and you get a coefficient of 2 on the even xi's, until we get all the way out to the last one, where we just get one of them. So the very last one is going to be, we have plus 4 f of xn minus 1 plus f of xn. And we do have to assume here that n is even. Strictly speaking, this comes from, we're not actually approximating with a parabola on each particular interval. I believe this comes from approximating with a parabola across 2 intervals. And for that reason, we have to say that n is even in order to get this. But this is what happens when you approximate with parabolas. Now, you could, of course, ask yourself, what if we kept on going? What if we approximated with degree 3, degree 4, and so on? Well, I don't know that people usually do that. We usually stick up. To my knowledge, we usually stick with Simpson's rule like this, but I'm sure you could, and I'm sure people have studied what happens when you use higher degree polynomials. Anyway, that's really what's going on here. You're approximating your function with parabolas on each piece of the interval that you're trying to integrate over, and this is what it works out to be. Now, the nice thing about Simpson's rule is the error bound that we get is substantially better in a lot of ways than the error bound that we got for the others, because the error, and let me make sure that I write this down, if the absolute value of the fourth derivative of x is less than or equal to k on the interval from a to b, then the error in the Simpson's rule, which I'm going to write as ES, is less than or equal to k times b minus a to the 5th divided by 180 n to the 4th. Now, this b minus a to the 5th, that's worse than the other rules, because for the other rules, we just had b minus a cubed. So in that sense, our error has gotten worse. But here's where our error has gotten a lot better. First of all, k is the fourth derivative rather than the second derivative. And for a lot of functions, the higher the order of the derivative, the more the derivative sort of calms down. I mean, that's not always the case, but for some functions, it's kind of the case. We usually don't have it where higher derivatives get more wild. So usually, if your second derivative has a certain bound, you can expect that the fourth derivative's bound is going to be no worse than the second derivative. At least that's our hope. Maybe it is worse. In some cases, it will be. Like, for instance, if you have certain exponential functions, then the fourth derivative's bound could be worse than the second derivatives or something like this in some cases. But here's where it's really good. Instead of just having an n squared in the denominator, it has an n to the fourth in the denominator. And that means we can get a much, much smaller error, or we change our error by a much larger fraction as we increase n. So by taking a somewhat larger n, we end up with a much better approximation. So as n gets bigger, in other words, for low values of n, this approximation might be just as bad as the midpoint or the trapezoidal rule. However, as we increase n, this gets better a lot faster than the midpoint or the trapezoidal rule does, meaning we can often get within a certain tolerance for error with far fewer calculations than we would with the midpoint rule. Consider like n to the fourth versus n squared. That's a big deal, because if n is 100, then 100 squared is 10,000. Now that seems like a lot, so we would be dividing the error for the midpoint rule by 24 times 10,000. Well, 100 to the fourth is 10 to the eighth, which is 100 million. So instead of dividing by 10,000, we're dividing by 100 million. That's actually 10 to the sixth better, or not 10 to the sixth, 10 to the fourth better than what we were getting with the midpoint rule. So the point is that Simpson's rule can give you a really, really tiny error with comparatively few subintervals. For this reason, a lot of computer algebra systems, when they do definite integrals by approximation, are actually using Simpson's rule. Now, again, the details of this derivation I'm not going to go into here because I don't think that they're really enlightening enough to worry about too much here. Honestly, you get Simpson's rule, it's kind of one of those straightforward but very tedious derivations where you say, okay, if I have a parabola and I have 3 points the parabola goes through, and we can therefore write down an equation for the parabola, because any 3 points will give you a parabola. I don't know if you guys remember that from pre-calculus stuff, but 3 points determines a parabola. We have 3 points. Let's take these 3 points and now calculate what is the integral of the parabola over this subinterval. Then we add up all of the results and we simplify it. And again, it's not like it's anything particularly difficult. It's just a bookkeeping, an algebra exercise, really, to figure all that stuff out. The error bound, on the other hand, is rather complicated. If you're interested in where that comes from, you really need to take a class on numerical analysis. I took such a class a long time ago, and I don't remember all the details of where this comes from. But the good news is that you can still use these things. Now, let me just say a thing about, in practice, how this works. So, usually, if you tell a computer system to do an integral, what that computer system will do is either it will do it for a fixed number n, in other words, a fixed number of subintervals, or you might be able to, with some systems, say, I want you to approximate this integral, and I want it to be within the following tolerances, in which case the computer system will just use this formula to figure out, well, what value of n do I need to pick in order to make sure that this comes out to be true? And once it has picked that, then it's going to It's going to just, use that value of n and give you back your answer. So whenever you're dealing with a problem that has a definite integral and all you need is an approximate answer, using a computer system to do a numerical calculation like this is an option. But there are limitations here, okay? So I don't want to pretend like this is a fix-all or like we should always just go to this. And the reason that there are limitations, there's two reasons, really. First of all, whenever you start approximating things, if you then use the approximation for another calculation, error compounds. In other words, if I have an approximation here that has a very small error bound, 3 steps later, that error bound could have gotten expanded quite substantially. So I may be within perfectly acceptable tolerances when I do this calculation, but if I then use this answer to do more calculations, I might go outside of tolerances. For this reason, it's always good to keep with exact answers as long as you possibly can, because it will cut down on the error that you end up with. The other thing that I want to observe is that a lot of times just getting a numerical answer will cover up really beautiful mathematical identities and facts that could otherwise show up for you. So for instance, when we look at that e to the minus x squared over 2 integral that I introduced earlier, remember it looked like this. It turns out that there are certain intervals over which we integrate this thing where it comes out to have a really beautiful exact answer, and you can find those by using techniques we haven't talked about here so far. They involve using multiple variables or complex analysis, but you can get certain definite integrals here for certain choices, and they come out to be really, really nice, and that would be hidden if all we did ever was to do these approximations. However, that said, there are a lot of situations in practical applications where an approximation is perfectly fine. So that's all I really have to say about using approximations here. I know we haven't done a lot of examples in this, but to see examples, again, the reason I'm not doing examples is because it's literally just plug stuff in and then add it up according to the formula. So hopefully you guys are comfortable evaluating a function and adding it up if you need to at this point. And you can look at the examples in your book for that kind of thing if you want to see more. So next time we're going to do something that I think is mathematically much more interesting. We're going to look at how we can make sense of integrals that don't necessarily admit Riemann sums. So there are some integrals that we think this integral should exist. Here's a definite integral. It ought to exist in some sense, but we can't really just do Riemann sums for it for one reason or another. These lead us to the notion of what are called improper integrals. And yeah, we'll be looking at that kind of thing and how we cleverly turn them into problems involving Riemann sums next time.